Hello and welcome to the next lecture of the module Decision Making for Autonomous Robots. My name is Marija, and in this lecture we focus on the problem of robot decision making. How can we get a robot to learn from its environment and adapt its behavior so that it can perform useful tasks even when the environment is very complex and unstructured? To address this challenging problem, in this lecture we look at reinforcement learning, which is all about having the robot or the agent experiment with its environment in order to receive some feedback and optimize the next best actions to take. Now, before we move on into the lecture content, it's worth mentioning that reinforcement learning is a very broad field and actively studied topic in robotics and artificial intelligence. As such, this lecture is designed just to give an overview and discuss the key elements that we need to actually start implementing reinforcement learning in robotics practice. So the point of the lecture is not to give an in-depth review of all the methods that exist in this field. And we cover two main parts of reinforcement learning called model-free prediction and model-free control, and the different methods that exist within them. And in the next slides, we look at exactly what this means. But before we move into that, at this point in the module, it's a good time to take a step back and appreciate a roadmap of what we have covered so far. So in the past few lectures, we specifically focus on the problem of robot motion planning. So in any of these scenarios of robots that we have seen many times before, how can we get a robot to move from one point in the environment to another in a safe and collision-free way? And we looked at different algorithms for doing this, such as search-based and sampling-based methods. Importantly, we made the assumption very often that the robot has no sensing and no actuating uncertainty, so that all the plans are executed perfectly in the real world. And we also assumed a perfectly known model of the environment so that we know exactly where the obstacles are so that we can do collision checks. Then we also had an introductory lecture on the more higher level problem of robot decision making. And now on the slide, we can see examples of different decisions that these robots need to make in their respective scenarios, which were covered previously. And intuitively, we specified the decision-making problem as finding the next high-level action that the robot should take. So for example, if this robot is currently at point A, we asked, where should point B be so that the robot can execute its mission most successfully and has the highest value of taking this next best action or movement. So for example, if this robot was in an inspection scenario and it's currently here, where should it go to take the next measurement so that it can inspect a structure most effectively? Specifically, in real-world scenarios, we said that we consider the problem of sequential decision-making. And this is simply when the robot does not plan only one step ahead, but has a horizon and needs to consider a sequence of actions that it should take. And our goal here was to optimize the sequence of actions that lead the robot to the maximum expected reward or the usefulness of its actions. And we said that there are several challenges associated of solving sequential decision-making problems. So first of all, the robot needs to think about the consequences of its actions. So for example, in the inspection case, if the robot already takes a measurement from a certain point and then goes around the environment and goes back to the point again, it could happen that the value of the second measurement is diminished because the robot has already acquired a measurement at the beginning of the mission. Another challenge that we pointed out is that the reward may be delayed. So the short-term actions leading to a certain reward might not necessarily correspond to the best thing to do over the longer term with a longer horizon. And again, from the decision-making lecture, we said that we're interested in the science of decision-making, and we captured the interaction of the agent and the environment using this interaction loop. So here the agent is the robot, or the entity which performs the actions, and the environment is everything else that is interacting with the agent that is associated with emitting observations, telling the agent about the state of the environment, as well as rewards. And we said that the reward was a fundamental quantity in the decision-making because it captures the value or the utility of different actions done by the agent. And then, given these quantities, we formulated a loop of interactions where the agent emits an action on the environment and thus receives an observation and a reward. And we said that this happens over time, over several time steps, to build a sequence, which we also call the experience of the agent during this mission. And we're going to use this experience in reinforcement learning so that the agent can learn the next best actions that it should take, as well as the value of different states in the environment. So this is just a recap of some of the variables that we introduced in the decision-making lecture that will be also useful now when we get into the discussion about reinforcement learning. So specifically, we looked at the framework of the Markov decision process, or MDP, which was a general sequential decision-making framework. So the Markov decision process, as we said, obeys properties of Markov dynamics. So this essentially means that the next steps of the agent and the reward that it gets for executing that action will be independent of its previous trajectory. So we can discard everything that happened in the past if we want to think about the future. And then we also have several other assumptions. So we assume that a fully observable environment where the robot always knows its state. So for example, in a grid world where the robot is navigating between the cells of a grid, this could be which cell in the grid the robot is at a particular time step. So we assume that this is fully known based on the observations that are emitted by the environment. We also said that we have stochastic state transitions which capture the actuation uncertainty of the robot. But we actually had a model for this. So if you remember, we designed tables that tell us the probability of the robot finding itself in the next state, assuming it is currently in a particular state and does an action. And we can tabulate all these probabilistic state transitions and then use them in order to find the best policies or the best actions in the Markov decision process. And we also had a reward function which tells us how good or what is the value of a particular action done by the robot. So these are some numbers and that we assume that we have in the Markov decision process when we introduced it in the decision-making lecture. And how did we solve problems that are formulated as an MDP? So towards the end of that lecture, we looked at dynamic programming methods such as value iteration and policy iteration, which are iterative methods of finding the best policy for the agent. And remember, the policy is essentially a rule book of what the agent should do, assuming it finds itself in a particular state, which action should it take next to lead to the most expected cumulative reward in the future. So this is all about how we can find actions for the agent, assuming we have a known MDP. So if we have a nice mathematical formulation of the state transitions and the reward, we say that we have a known model of the MDP, and we can actually use this value and policy iteration algorithms by doing mathematical manipulations. So we can formulate equations and use an iterative approach in order to find the solve for the optimal policy. So this is essentially where we stopped in the decision-making lecture. And when we talk about reinforcement learning, we're going to question the assumptions of having known stochastic state transition models and reward function models. Because these are very heavy assumptions in the real world. For example, if we have a self-driving car, we have to tabulate all the possible, for example, steering actions that the robot could take and find a way of enumerating all the states that the agent or the robot could find itself in next. So you might imagine that in this case, there are not only extremely many states that the robot can find itself, which would be very difficult to implement if we want to solve the problem numerically and iteratively, but there also might be various sources of uncertainty that are difficult to capture in a simple way using mathematical equations. However, this doesn't mean that the sequential decision-making problem is not there. It simply means that we have less information and we don't have the clear formulation of the MDP in front of us. So reinforcement learning is a very exciting topic that deals with how can we actually solve for policies of the robots in these scenarios. So if we have an underlying MDP, but we don't know everything about it, so we don't specify our state transition and reward models, how can we learn from the agent's actions or the interactions in that loop that we saw on the previous slide in order to figure out what are the next best things the robot should do? And this essentially captures the essence of reinforcement learning and motivates why we would want to use this approach in situations where dynamic programming is inapplicable. So going into more detail on what reinforcement learning is about, as we said, we want to learn from interaction. So we want to look at the loop, that experience that the agent has collected during its mission and use that to do some learning on what the environment states look like and also what are the next best things to do. We assume that we have some feedback from the environment only in the form of a reward signal. So reinforcement learning would be meaningless if we don't have some measure of what are good actions to take. So it's essential that we have something that tells us, so when the agent has done an action, is that action good or bad? This is captured by the reward value, and this is all that we're going to be using to do reinforcement learning. Reinforcement learning is valuable because, as we presented in the self-driving car case, it can handle arbitrarily large MDPs. So we don't need to worry about creating a big table of all the possible state transitions and the rewards that the agent might get in memory. We can operate directly on that experience and the sequence of interactions of the robot and its environment, and use algorithms to learn from that. So it saves us the effort of storing actually a model of the environment and how the agent interacts with it. Reinforcement learning is often very attractive because it also resembles human-like learning. So if we think about a toddler that's learning how to walk, this doesn't just happen by itself. The toddler needs to experiment with different actions for standing upright, maybe grabbing onto something or obtaining some type of support from an adult, and then eventually it will learn which actions it should do so that it can walk successfully, and we can say that the reward captures the success of being able to walk. So just like a toddler interacts with the world around it, we want a robot to interact with the environment that it lives in and draw this parallel there to establish the concept of learning and artificial intelligence in these situations. Again, our objective, as in dynamic programming, is always to find the optimal actions. This is everything that decision making is about. It's finding the best things to do. Except now, our aim is that we only want to do this with this limited feedback and in a model-free way. So this sets up some of the basic principles of reinforcement learning and motivates the reasons why we want to use these types of approaches. So further, here are some frequent examples of reinforcement learning in robotic applications. So one commonly addressed problem in current research is how we can get robots, for example, to learn how to walk or run, just like the toddler. So here we ran different simulations where the robot was executing particular actions, and in some situations it fell over, in some it walked a little bit, in others it actually managed to run quite a far distance, and we had some reward that captures the value of all of these actions. So if the robot fell over instantly, then we would have negative or a very low reward, depending on how we define our problem, associated with that outcome. Whereas if the robot managed to run successfully for a very long time, that would be a sequence of actions corresponding to a very high reward. And eventually this robot has actually learned from that experience and from trying new things, which actions it should do in order to run successfully, and here we see a successful run. Another example is that of self-driving cars. So consider if we want a car to follow a lane. Without us actually doing anything, the robot car is actually doing this by itself. So what we see here is a visualization of Deep Drive, which is a simulation environment for self-driving cars. And in this environment, we have different scenarios, different cities, different structures of streets, etc. And we can perform different actions by the robot in an autonomous way. And we have, for example, in the case of lane following, a reward associated with how successful it is. When we do these actions, how much do we actually manage to stay in the lane? So here we see examples of different scenarios, and then what we do in reinforcement learning is we use the simulation to learn. So again, we need to acquire some experience for reinforcement learning to make sense. And in the case of self-driving cars, we can use this simulation environment to acquire that experience and design the policy. So the reason why we do this in simulation is hopefully quite obvious, is because crashes and other unsuccessful policies will be rather costly and dangerous in the real world. So this example shows how we can use a simulation to learn and design these policies, and then we could have, for example, a simulation to real algorithm which transfers the domain from the simulation to the real world and accounts for the changes, so that we can also deploy these policies there. And so this gives us some insight as to how we use reinforcement learning in practice, and hopefully gives a very exciting picture of the possibilities of the things we can do with these algorithms. Because, for example, robots learning to run by themselves and also to drive by themselves, I personally find quite exciting. So this brings us to reinforcement learning and the two main parts that we're going to look at in this lecture. And these concepts are very distinct, but they're also related. So we look at model-free prediction first, and then model-free control. So by model-free prediction, we are going to learn how to estimate the state values of an unknown MDP. So assuming we don't have that state transition table, we want to figure out how much value could the robot get from being in a particular state. So how much expected reward can we get? And remember, in the decision-making lecture, we specified the state value in this way. So how promising is it for the robot to be in a particular state? And the semantics of prediction here are connected to the fact that we're trying to predict or forecast the future reward, assuming we're finding ourselves in a particular state. So model-free prediction is all about designing algorithms that enable us to uncover or to estimate these values in a situation where we don't have a model, or in other words, have an unknown MDP. And then in the next part of the lecture, we're going to see how we can use ideas from model-free prediction to enable model-free control. And model-free control tries to optimize the state values. So rather than just figuring out what is the value of a state, we want to do control. We want to optimize the state values by finding the best possible actions. And again, we do this in the setting of an unknown MDP. So an overview of what the next steps will be in this lecture. First, we want to figure out how to compute the state values of an unknown MDP if we're given a policy. And then we're going to try to change the policy and optimize the state values. We start by looking at methods for model-free prediction, which is trying to figure out the state values of an unknown MDP if we have a fixed or given policy for the agent to follow. In model-free prediction, the first class of methods we look at is called Monte Carlo sampling-based methods. These methods are simple, not the most efficient, and yet widely used in practice. The main idea behind Monte Carlo sampling is to repeatedly perform random sampling to obtain the likelihood of certain results occurring in an unknown distribution. So if we have an unknown distribution and we sample from it enough times, we will eventually converge to the true distribution. This is the key concept there. And this is very related to our lecture on sampling-based methods, where we did not explicitly model the connectivity of the free space in an environment, but rather we tried to sample from it and we derived methods that are probabilistically complete. So if we sample enough times, we can find a safe path for the robot to follow as a solution to the robot motion planning problem. So this idea of random sampling is also relevant in that context by giving algorithms that give probabilistic completeness. The same thing is happening with Monte Carlo methods. So to make this more concrete, let's look at a very simple example of how we can estimate the numerical value of pi. So here is one approach using Monte Carlo sampling. We can draw a quadrant where we have unit extent coordinates in each direction. And then we can simply sample within that quadrant by drawing random vectors within the range. So one could also imagine this as just closing our eyes and throwing darts and seeing where they will land in this quadrant. And then we can count all vectors that we obtained from sampling that have a distance of equal to or less than 1 from the origin here. So we want to see in terms of Euclidean distance how many will actually have that distance with respect to the origin. And this value that we counted, we can then multiply by 4 in order to obtain pi, because here we're also only considering one unit quadrant. So visually that will look like this. So here we can see red points which correspond to vectors that were sampled satisfying the distance condition, and the blue ones are the ones outside. And as we increase the number of samples, we populate the unit quadrant and we get closer and closer to estimating the value of pi. So over here on the top we can see the value starting from 3.11 and eventually converging to 3.14 as close as possible with increasing number of samples. So the more samples we obtain, intuitively, of course, the closer we are to the actual estimate of the quantity that we're interested in measuring. So how does this apply to reinforcement learning? So we want to use Monte Carlo reinforcement learning in order to learn from episodes. An episode is, remember, nothing but a sequence of state, action, reward time steps that we can then chain together. And we call this sequence an episode or an experience from which we want to learn from. And we say we have episodic behavior, which, remember, this means that eventually the episode will terminate after a certain number of time steps. So there is a very clear termination state that we reach at the end of the episode. So if we have an episodic task, we can compute the return associated from a particular time step. So defining the return, again, from the decision-making lecture, this is simply the expected rewards that we will get from this point on until the terminal state. So this is the cumulative expected reward in the future. And this concept is important when we now look at how we can apply Monte Carlo methods. And here, when we talk about returns, remember we also have usually a discount factor, which is associated with downweighting future rewards. So we say that the rewards we get in the shorter term are more important, and we apply this decay factor to decay the value of future rewards. And so that is defining the return. So in model-free prediction, we have an unknown MDP, so we don't know the reward function and the state transition functions, and we're trying to estimate the state value function of each state. So remember, the state value function mathematically is defined the expected reward that we can get from being in a particular state. So if the robot is in state S, we can estimate the reward, the expected return from it being in this state, and this, if we have a fixed policy, corresponds to the state value function. Now, model-free prediction is all about trying to estimate the true value function when we don't know the MDP. So the basic idea we have here is to sample the expectation by calculating the mean return over the episodes. So if we have different episodes that were extracted from our MDP, and we have returns corresponding to particular states, intuitively, we want to tally up these returns corresponding to the states, and we want to find the average. And the average will be the best possible estimate that we can obtain by Monte Carlo sampling methods. So essentially, we're just calculating the mean. So we're saying if we have observed all of these episodes, all of these, for example, trajectories of the robot moving in an environment, we can estimate the state values by looking at how much reward, how much future reward, so how much return was obtained from the states of these trajectories, average over them, and we get the best possible estimate. So this is how sampling comes into play in Monte Carlo reinforcement learning. So let's formulate this mathematically now. We look at two slightly different flavors of Monte Carlo sampling. So the first one is called first visit Monte Carlo reinforcement learning. So we said we have a series of episodes, and if we have a state appearing in an episode for the first time, what we're going to do is increment a counter saying, aha, we observed that state, and we're going to accumulate the total return that we got from being in that state over different episodes. So we accumulate how much return we got from the state, and we keep track of how much time the state was visited. And then we simply find the arithmetic mean, so the total return divided by the number of times we have visited that state. That will give us an estimate of the state value. And if we have enough episodes and the state has been visited an enough number of times, we can prove that this will actually give convergence to the true state value that we saw on the previous slide. So the reason why we call it first visit is that we only update these variables if we have visited the state for the first time in this episode. So if the robot is traveling, say, in a loop and visited a particular point, the next time it comes back to that point, or let's say that state, then we don't do this update procedure. So we only account for the first time that we have seen that state when we actually calculate the mean. An alternative approach, as one might expect is to consider every visit Monte Carlo reinforcement learning. So every time we visit the state, regardless of whether we're doing loops or not, we want to increment our counter and sum up our return at that point to our total return. So mathematically, everything is the same. The only difference is that instead of seeing that state for the first time in an episode, we actually do this every time. And which of the two methods are better to use? Well, this really depends on our application, because both are completely valid, and the key requirement is that the state actually appears enough times so that we get enough information from it so that the mean actually converges over time. Otherwise, if we don't have this requirement, of course, Monte Carlo sampling would not have enough samples and the law of large numbers would not apply. So over here, what we did is we run a bunch of episodes and we tally up the information for the state, and we also keep track of the number of visitations. Now, moving towards more online planning, can we do this during a particular episode? So as an episode is executed, can we update these values incrementally rather than waiting for all of the episodes to finish and then computing the mean? So the answer is yes, we can. We can keep a so-called running average by incrementing the counter and then looking at the return and adjusting our current estimate of the state value. So over here, what we do is we say that if we have a new return corresponding to that state and a previous or like the current estimate, then we can compute the error between them and just nudge the current estimate that we have slowly in the value of that error. And if we want to keep track of all the times we have seen that state before, we also need the counter. So this is just a way of updating the average in an online way, not waiting for all of the episodes to finish. An important thing to note here is that we have the estimate of the state value, and then we have this term here, which is the difference between what we have seen of the state value, so the return at this time step, and our estimate. And the difference between them is called the error. So we try to change our value or current knowledge by the error by a small amount. And in this case, we want to keep track of the average over all times. And this idea of changing a value depending on the error, a small amount in that particular direction, is one which we will see many times throughout this lecture. So it's worth noting that at this point. Now, what if we want to add an element of forgetfulness? So let's say we don't want to account for all the times that we have seen the states in all the episodes, but rather we want to keep a track of an average of the past, let's say, X times or Y times that we have seen the state. This could be relevant, for example, if the reward changes over time and we want to add an element of memory to only keep track of the most recent times that state has actually produced a return, or that state was observed in our episode. So what we can do here is replace our counter. So rather than being interested in all the times in all the episodes that that state was observed, we can add a value alpha that determines what we want this memory to look like. So how many previous states encounters we want to take into account when we consider our running average in the incremental update. So the premise here is exactly the same as in the Monte Carlo methods of the previous slide. The only difference is that we're using online updating using this incremental structure. The main concept of sampling and computing the state value from the samples is the same. An important thing to note, however, is that we need to wait for the episode to finish in order to figure out what the returns will be. So if we see a state, we assume that the episode has reached completion so that we can use our return for that state. And later on, we look at methods where we actually don't need to consider episodic behavior when we estimate state value. So Monte Carlo sampling looks great so far. So we learn how to use it in the context of reinforcement learning for model-free evaluation. So can we take it a step further, and can we follow our logic of the decision-making lecture in order to use Monte Carlo methods to actually solve MDPs? Remember, solving MDPs is associated with decision-making. So rather than just estimating the state values, we want to see what's the optimal state value for a given state. So we want to know if the agent is in a state and did the best possible thing next, what is that state value? Can we use Monte Carlo sampling to do that? So far, we only looked at episodes that we got from policies, from given policies that may not be optimal. So we have a certain number of trajectories, episodes, and we could plug them into our Monte Carlo sampling, either using the non-incremental or the incremental update strategies in order to compute the state values. But is there a way of finding the best policy? So if we recall the material from the decision-making lecture, we formulated our optimal value function as follows. So the best possible state value that we can expect from a given state S is simply the next action, the next best action, so the highest reward action that we take from that state, plus the expectation over the state value of the next state. So this is simply Bellman's equation. Because we try to decompose the problem, we say that the best possible reward that we can expect from this state is the next best reward if we were to take the best action and the best value of the next state. So the state that we enter having executed that action. So what we try to do now is try to couple these ideas. So Monte Carlo sampling and optimal value function. Do these two ideas somehow connect together, and can we use sampling to actually figure out the best policy, the best value function? So unfortunately, we run into the same issue as in the decision-making lecture, is that we have this maximization operator here. So what this basically tells us is that we need to look and see what is the maximum reward that the agent can expect if it executes a particular action. So this corresponds to the optimal action. And this is exactly why we needed iterative methods such as value iteration and policy iteration in the decision-making lecture to solve problems in dynamic programming. Because we have a non-linearity here that we could not address using algebraic methods. So instead what we did is we tried to incrementally improve our state values and our action values using value iteration and policy iteration. So for Monte Carlo sampling, we have the exact same issue because we can't, sampling is not applicable for element-wise nonlinearity such as maximization. As we said, sampling and the law of large numbers in general is very useful for us if we want to compute expectation. Because this tells us that if we sample enough times, we know what the underlying distribution looks like, so we know an average. But maximization is unfortunately hard to find, so this limits the applicability of Monte Carlo sampling, and we can't transfer these ideas to the decision-making domain. In the next part on model-free control, we actually looked at how Monte Carlo sampling fits in. But Monte Carlo value iteration, at least in this context, is not possible to implement. So we have now some understanding of Monte Carlo-based policy evaluation and model-free prediction. So let's consolidate our discussion of it by looking at some of its benefits and limitations. So because it relies on simple sampling and arithmetic operations, then Monte Carlo sampling is relatively hassle-free to implement. All we need to do is keep track of how many times the agent has seen the state and update the state value function accordingly if we're provided with all these episodes with certain policies. And also, by the law of large numbers, we can say that Monte Carlo sampling is relatively insensitive to values of the initial state values. So if we have some guess as to what the state values are, and we sample enough times, eventually we will converge to the true values. So we don't need to worry about what initial conditions, because we have the law of large numbers in our favor with the sampling properties. However, a key disadvantage that we already hinted to is that we need episodes. And episodes are necessary because we looked at the returns the agent gets from being in a particular state. So we need to have actual access to all the information along that trajectory, for example, in order to apply Monte Carlo sampling. So that information already needs to be there. So if we have non-episodic environments, we can't use this approach. And another issue arises with regards to efficiency is, what if we have very long planning horizons? So what if our episodes are especially long? Then the sampling-based strategies will take quite a long time to perform the update, and this might not be suitable for real-world applications. Another issue could occur if only sparse rewards are provided as feedback. So, for example, if we do a lot of actions and we only get information about, let's say, if a game is won or lost at the end, but meanwhile we executed many moves and we have a long planning horizon, it will be very difficult for our algorithm to correlate the usefulness of a particular state to the final outcome. So this is why it's better to keep the number of states in an episode small and also receive rewards more frequently, so we can more easily form that association with reward and the state. Otherwise, we need a lot of samples and convergence will be much slower to the true state value functions. So now we're going to try an alternative approach and see how can we address non-episodic environments if we want to solve exactly the same problem. An alternative class of methods for model-free prediction is called temporal difference, or TD learning. And here, exactly the same, we want to achieve model-free learning of the state values. However, this time we also want to be able to learn from incomplete episodes. So we want to sort of update the state values on the fly rather than waiting for all the episodes to finish, as we did with Monte Carlo sampling. So how can we do this? So one key idea is that we don't need to wait for the episode to finish. We can work with partial information and partial trajectories, let's say, for the robot. So consider this example. If the robot is at a particular point, A, and wants to go to B, and we execute an episode, and we can use that for Monte Carlo learning. Now, the main idea on temporal difference, or TD learning, is to say, well, what if the robot is in a state in between A and B? Can we actually use that information in order to update the state value back at A? We should have an estimate of this state if we're keeping track of all the states in our MDP. So rather than looking at the actual rewards that we get for executing that episode, we say from A, if the robot takes, let's say, one step forward, and we can see that reward, and then we can look in the future and use an estimate of this intermediate state from the intermediate state to B in order to use in our decision-making algorithm, or a TD learning algorithm. So we want to use the fact that we actually have guesses at intermediate states to achieve learning, and we don't have to wait for all the episodes to finish. This becomes clearer when we look at the mathematics behind it. So here we see the TD0 algorithm, and we look at exactly what the 0 means here a few slides from now. So if we have a time step t, not an episode, but simply a time step within an episode, what we can do is look at the state that we're in and then perform an update of the state value based on our current value, so what we already estimated about that state, and the reward that we get from taking one step forwards plus the next estimate. So this is the next state. This is exactly the main idea behind Bellman's equation, remember, because we try to decompose the value of a state into the next action and the reward from that point on encapsulated in that state value from the next state. So we can think of our estimate of the next state as kind of summarizing all the future information that we don't have access to yet because we didn't execute the episode entirely as in Monte Carlo learning. Okay, so basically this gives us a method of actually updating the state values at each time step, even for non-episodic environments. Here we call this red part, so the next reward that we get from executing an action, and the next estimate of the state value, the TD target. And we call the difference between the TD target and our current estimate of the state that we're in as our TD error. We have an alpha here that basically adjusts how much correction we want to make to the state value. So exactly in the same way, we're trying to update an estimate that we currently have based on an error, and the error is based on the target, which then uses these principles of decomposition. So we see again this familiar structure of updating a value based on the error by a small amount dictated by the alpha. The alpha is simply a parameter that we set, for example, it's similar to in stochastic gradient descent, how much we want to move in the direction of the gradient. So this gives us a way of doing learning in episodes that are not complete. And this idea of using the trick of the next state estimate instead of looking for all the returns that we actually get from the episode is called bootstrapping. So we want to exploit the fact that we have a next guess in order to update our current guess. And this is what this temporal difference algorithm is all about. And this is the key idea behind bootstrapping. So having looked at two important methods for policy evaluation in reinforcement learning, Monte Carlo and temporal difference, which are at different extremes in terms of how they update the state values, now we're going to see if there are ways of combining them in order to get advantages and more robust and better performance. So on this slide, we can see an overview of the two methods that we considered, TD or temporal differencing and MC or Monte Carlo based sampling. So as we said, TD leverages bootstrapping in order to perform one-step updates in non-episodic environments. In this way, for the state values, we can get lower variance estimates and also faster convergence because obviously we're updating the state values at each time step, unlike in MC-based methods where we have to do it at the end of an episode. TD-based methods, however, are, as expected, sensitive to poor initial value guesses for the state values. And this is because bootstrapping basically exploits the estimate of the next state value when we try to update the current state value. And if our next estimate is inaccurate, then convergence will be slower. And finally, the bootstrapping formulation also exploits the Markov property, where we saw a very similar structure as in the Bellman equation occurring when we formulated our TD target and TD error. In contrast, MC sampling gave us very different properties by learning only after episodes are terminated. So because we use random sampling and the law of large numbers, we can obtain unbiased or low bias estimates with high variance depending on how many samples we take. And eventually, due to the slow bias, we can eliminate any poor initial value guesses, since we don't rely on any internal estimates that we have as in TD methods. And also, these are the preferred methods to be used in non-Markovian learning environments, even though in the majority of the lecture here, we consider MDP-based formulations. So these are the two methods that we covered, and already we see that they lie on different extremes, either waiting for all the rewards to come back in form of returns, or doing one-step updates based on bootstrapping. So we end up with this kind of spectrum, where TD performs one-step updates and MC on the other end waits until the terminal state is reached. So we start to think, is there a way of actually performing a different number of steps in between? So if we execute our episodes for 2, 3, or say n steps, and then from that state on, we can use that summary of the estimated state value by bootstrapping. So these are the idea of this method's so-called n-step prediction that lie in between the spectrum. So what we have here is an ability to change the number of steps that we take and observe the actual rewards and how much we want to estimate. So this gives us a way of obtaining some intermediate behavior between TD and MC. However, obviously, the question arises, how many steps should we take? So if we have a reinforcement learning problem, we want to see what are the properties of this intermediate step, so which one might be beneficial to use in a particular case. So mathematically, this is what n-step prediction looks like. So with one step, we have TD learning, which bootstraps of the next state value estimate, whereas on the other extreme, we have MC methods, which go all the way collecting the actual returns until the terminal state. And in between, we have the so-called n-step methods. So formulating the n-step return mathematically, we can say that we wait for a certain number of steps, observing the actual reward with the discount factor, and as we said the rest, we can just summarize using the state value function after the n steps have been completed. Now, what we do in n-step TD learning is to exploit these returns instead of our TD target. So again, we have exactly the same mathematical structure where we have our current estimate of the state and we have this error. However, instead of now only considering the one-step TD target with one actual return, we can change this to any number of steps by using the corresponding return. So we accumulate the rewards for a certain number of n steps, including the discount factor, and the rest we bootstrap. So this is the basic idea behind n-step TD learning, and our algorithm before TD0 was actually corresponding to a one-step version of TD learning. And again, we have this alpha parameter here, which says that we only want to perform a corrective action on our current state estimate in the direction of the error by that amount. So this controls our convergence properties. So again, we come to the question of how do we actually select n for a particular problem? And now we introduce the methods that rely on lambda returns. So we find by running experiments that picking one particular number of returns to calculate in the n-step return, so picking a number of n, is not very robust across different scenarios. So we try to think, how can we do better? And this involves actually incorporating all the possible scenarios of the n returns. So again, over here we have our one-step return corresponding to TD0, and on the other end, the MC. And the n-step returns in the middle, what we want to do is take an average of them. So we want to combine all of our n-step returns into a nice, simple mathematical formulation by taking their mean. So what we do here is we introduce a parameter lambda. And for each of the n-step return, starting for 1, we multiply it by lambda. Lambda is a value between 0 and 1. And then we just take the mean. So we try to formulate the geometric mean taking into account all of these possible scenarios. Lambda is the parameter that controls how much of these n-step returns contribute to the final return. And the reason why we multiply it, as we see on the next slide, is because we want to essentially decay the value of future rewards. So we want to say that we place more value when we do the one-step return. As we progressively do more returns, we give less value to those returns. And this gives us a nice and elegant, simple mathematical way of actually incorporating all the possible scenarios. And here the reason why we have this 1 minus lambda is simply a constant to make sure that all the weights here based on lambda are actually summing up to 1. So what we can do here now is take our lambda return. So lambda return is nothing but a geometric mean of all the possible n-step returns. And we can substitute into our update equation, which is already familiar. So the structure of the update equation in TD Learning stays exactly the same. So we still are looking to refine our estimate of the state value. The only difference is how do we actually define our error. So a return in this case is our lambda return, taking into account all the possible n-step returns. So this is just compressing all this information based on a parameter so that we can perform the update in a more complete way, accounting for all the possible scenarios. So if we plot this lambda parameter, how does it actually look like? So we already hinted at the fact that lambda is a decay factor. So the more steps we do, we want to try to discount the value of information in the future. So this is what our lambda parameter does. So if we plot it from the previous slide, we can see an exponential decay based on the number of time steps that are executed. So on the x-axis, we can think of sort of n, or the number of time steps, and we can see the weight reducing. And the total area, of course, sums to 1 because we added that constant there, 1 over lambda. And the reason we want to do this is because we want to trade off between short-term returns, which we say are more high priority, and long-term returns, which we discount with lambda. The main intuition here is rather similar to the discount factor, remember when we formulated the returns. So by multiplying all the future rewards by a discount factor, we were able to mathematically capture the intuition that we want earlier rewards to have higher weight compared to those that come later on in the episode. And on the bottom of the slide, again, we can see our update equation based on the lambda returns in so-called TD lambda reinforcement learning. So the purpose of adding this lambda factor is to account for the recency of the returns. So we want to add this time element and say how important they are according to the number of steps that we take. So we try to improve on our simple Monte Carlo and temporal difference algorithms. So recency is one aspect. So we said that TD lambda assigns larger weights to states that are more recently seen, so closer to our current state. However, what if we have many episodes and we see a state more frequently? Can we also take that into account somehow? And here we come to a new concept and modification to our algorithm so far, which is eligibility traces. So intuitively, we want to somehow keep track of how much does a state contribute to the reward. If we saw that state many times, we want to say intuitively somehow that that state had a large effect on what we saw at the end of the episode or the reward that we get. So here we have another mathematical trick on the concept of eligibility traces, which basically captures the fact that each time we see a state, we want to add priority to it. So we say that if that state was visited more times, it is likely to have more influence on the final solution. And this is a mathematical way of formulating that. So we say that here on the bottom of the x-axis, the number of visits to a state, so the number of times that it was seen during an episode. And each time we see the state, we can increment its importance by 1. So this is a factor that we can specify. So early on in the mission, what was happening, or in the episode, what was happening is we saw the state 4 times and we gradually increased its priority. And when we don't see the state over a certain number of time steps, we use lambda to decay its importance. So this is just by saying if we go for a long period of time, for example, between the 4th and 5th visitation without seeing the state, lambda controls the fact that the value of this state, its eligibility, its contribution to the returns kind of decays. So this is a way of putting together our concepts of lambda returns and eligibility traces into one formulation. And of course, we start with 0 eligibility returns simply because at the beginning we have not observed that state, so it does not contribute towards our final reward. So how can eligibility traces be incorporated into our TD lambda algorithm? Well, here we have our TD error, which we have already seen before. So this is our TD 0 error, actually, which only accounts for the reward after 1 step and then follows the bootstrapping. So this is the kind of correction that we want to make to our current estimate of the state value. And now, in our TD lambda update rule with eligibility traces, we have that error as before and we multiply it by the factor that is the eligibility trace. So intuitively, we have now this new term, which, as we saw in the previous slide, takes into account the responsibility of the state in generating that outcome. So in this eligibility factor now accounts for the recency by lambda, as well as the eligibility or the frequency, which we get by incrementing it every time that we see it. Again, the basic update follows the exact same mathematical structure. So we have an update in the direction of the error, with now this new factor, which tells us how recent and how frequent are the states that we have seen. One thing to note here is that by adding all of these additional things in the mathematics, we now come up with several constants that we need to specify for our algorithms to work. So now we have alpha as well as lambda, and also the discount factor. And these all interplay with each other. Changing them will have some effect on our algorithms' work, but it's important to figure out when we design the algorithms how they actually relate to each other and how much influence each of them exerts. So from the point of view of the update, this is just an illustration showing that we have this sort of backwards view. So we look at the states that we have visited from a particular time step. We have an error associated with each state as well as its eligibility, and then we use that in our TD lambda update rule. So this is a so-called improved version of our algorithm, which also takes into account the recency and frequency. So how does this look in pseudocode? So here is a very simple mathematical implementation of TD lambda with eligibility traces. So at the start, we can initialize our state values, say arbitrarily, assuming that all the states are visited enough times, then we can say that we converge to the correct state value functions. And then for each step of the episode, we calculate our TD error based on our estimate of the state value, the reward that we have seen by performing an action, as well as the bootstrapped value of the next state. So we have the sequence of state, reward, next state that we incorporate into our TD0 error. And if we have seen that state in our episode, then we also increment its eligibility value. So remember, that was that spike that we saw when we saw the new state in the episode. The same state in the episode, sorry. And then importantly, for all states that we have in our MDP, we need to perform the update. So this happens not only for the states that were in that episode, but for all the states. Why? This is because the eligibility trace needs to account for the decay as well. So as we can see here, the eligibility trace therefore will weight the states that are in the episodes more, but also make sure that we add this decay or this forgetfulness of states that we haven't observed in that episode recently. And then we can repeat this for each step of an episode, loop through it, and as we said, assuming that the states are seen enough times, we converge to the correct values. Up until this point in the lecture, we looked at methods of evaluating a policy in an unknown MDP, assuming that the policy was given to us in advance. In this next part of the lecture, we move on to the realm of decision-making and see how we can give the agent the ability to choose what to do next in order to maximize the expected cumulative reward in the future. We call this concept of improving policies model-free control, and the word control is appearing because the agent can now decide by itself on how to maximize the expected returns. So in this part, we bring in the techniques on model-free prediction from the first part of the lecture, and we see how we can use them to evaluate policies and then try to improve them in order to achieve optimal behavior. And as before, we consider a model-free setting in reinforcement learning where the agent doesn't know anything about the environment, the state transitions, or the reward generation mechanism. So let's consider the idea and the motivation behind the policy iteration approaches in dynamic programming. So policy iteration, as we said in the decision-making lecture, came about by observing that the agent is not necessarily interested in all the state values of the MDP and discovering them, but rather only in developing the optimal policy. And remember, the policy is the decision-making part that tells an agent what action it should take next if it finds itself in a particular state. And based on these ideas, we moved from value iteration to policy iteration, which tries to incrementally improve the policy the agent is following to execute a particular task. So we said that policy iteration takes two steps: policy evaluation, where we try to evaluate and see what the value is of a given policy, assuming we follow it, and policy improvement, which is fundamental step trying to optimize the policy based on the expected returns. And the way that we evaluated the value of a policy was looking at this action value pair, which tells us what is the expected value if the agent follows a policy, assuming that it finds itself in a particular state and takes an action next. So moving on from value state values, we have now the concept of action values, or Q values as we will call them in this lecture, where we couple a state and an action to a value or a utility. And policy improvement was always about trying to maximize the Q value. So the reason why we recap policy iteration now is we're going to see how we can apply this, an analog of these ideas, in the setup of model-free learning. So for policy evaluation, we can already notice that this is similar to what we were trying to achieve with model-free prediction, where we have a policy and try to figure out what is the value associated with that. And next, we're going to try to see how to implement the policy improvement step in unknown MDPs. So talking about policy improvement, we have a very unique problem arising when we don't know anything about the environment. So assuming that the agent doesn't know about the underlying model of the environment, that has to learn from experience, and this is the definition and the main idea behind reinforcement learning. So we observe some interactions and we use that experience or that sequence of state action rewards in order to figure out what promising things to do are. This was our premise. So a fundamental dilemma that arises is that the agent in an unknown environment needs to decide whether it should explore or exploit. Well, so let's look at an example of this. Say we have a robot here and it's trying to go to a restaurant. So it has two options here. It can either go to the usual place, which is the restaurant that it knows, it's familiar with its favorite dishes, or it can go to an entirely new restaurant which looks very attractive and is having a grand opening now. So in this case, the agent has two options, and the one with the known usual place, it can go to and it knows what it's going to get. So it has already information about that restaurant, and it can use the information to exploit the best decision given everything it knows about the current situation. So this is like the safe choice. We know what we will get if we go to this location. However, an alternative is to explore, so to try something new and gather new information. And essentially this could be either better or worse than our alternative exploitation option, but at the time of making the choice, we don't know. So we have to decide which of the two things we want to do. And this dilemma arises very often in learning problems in unknown environments, and we're going to see how this relates to the ideas of policy improvement and having the agent learn optimal behavior in model-free control. So this idea of picking between known information and gathering new information is what we call the exploration-exploitation dilemma in robotics and artificial intelligence. So one simple thing to do if we think about a policy that wants to capture exploratory as well as exploitative behavior is, let's say we have a policy, and with high probability we want to exploit. So we want to go to the best possible next state, so we want to pick the next best Q value just by taking the maximum. So this corresponds to our exploitation option. But with some other smaller probability, we might want to try new things. So we might want to execute a random action and see if they take us to a better place. We call this approach epsilon greedy because it operates with a probability that we specify when deciding whether it wants to explore or exploit. So we call epsilon in epsilon greedy the exploration rate. So if we have a high epsilon, it means we pick random actions more often, so we try new things and we explore. And this might lead us to discover new promising actions, but if our epsilon value is too high, it might cause us to converge more slowly because we're not exploiting enough information about the environment that we already have. In contrast, if we're often exploiting, so if epsilon is too low, and most of the time we just go for the next best option that we know we have, then we might have suboptimal convergence because our algorithm is not encouraging the agent to explore unknown parts of the problem space. So typically epsilon, for example, in the range of 0.1 is a good compromise between exploration and exploitation. And of course, epsilon greedy is always based on a table of these Q values, so the action values for each state action pair. And we look in our table, and if we decide to exploit, we look at the value that's highest associated with our current state and simply follow that. So this is how epsilon greedy would look from an implementation perspective. So that is one method of improving the policy, so adding some exploratory behavior. So if this is our step of policy improvement, and we use some of the previous methods that we looked at in model-free prediction for policy evaluation, can we put them together to achieve model-free control? So for example, let's say we have an episodic behavior, the agent executing different trajectories, for example, and acquiring episodes in the environment. So after every episode, what we could do is we look at the policy that the agent has followed and evaluate it using Monte Carlo sampling-based strategies. Remember, Monte Carlo was episodic. And then we have our information about the state value pairs, and we can try to improve our policy by following epsilon greedy. So epsilon greedy includes this element of randomness that makes sure that we're not always following the same deterministic policy. Instead, we're trying to explore new actions and try to improve it. So what we will see here is that if we start in a particular state and we gradually improve our policy through the epsilon greedy algorithm, our Q values and our policy will converge slowly to the optimal values. And the reason why this happens is we're always keeping track of the best possible values, and we're trying to improve them with the epsilon greedy approach, using Monte Carlo sampling as our mechanism to evaluate policies. So this is essentially the exact same logic as in policy iteration, this two-step approach of policy evaluation and policy improvement. The fundamental difference here is that the agent does not know anything about its environment and is operating in a model-free way, so it needs to explore new possibilities and see whether they lead to better outcomes. So this is how one would implement model-free control in a simple way using MC sampling approaches. However, as we already discussed, MC sampling has certain disadvantages. So for one, it's only applicable to episodic environments, and it can have a very high variance if we don't have enough samples in an area or a particular state. And it's also very difficult to implement online. So it's impossible to update the policy after each step. And for this reason, we look at an alternative way of using the temporal difference, or TD learning, to evaluate a given policy. So this is conceptually exactly the same as the difference between MC and TD for policy evaluation. Key difference now is that we have this aspect of policy improvement where we try to actually sample new promising actions using epsilon greedy. We follow the exact same two-step approach as in policy iteration, and we can expect the same converging behavior. Our motivation for including TD learning here is to try to get faster convergence by performing updates after every single step, rather than waiting for a necessary episode to finish and then executing the sampling procedure. So to summarize, what we included now is in TD learning this epsilon greedy, which actually caters for the fact that our actions are not deterministic, so that we're trying to evaluate new promising actions to take. So this is that's it for in terms of model-free control. So the conceptual overview is there, and if we iterate enough times, we will eventually converge to the optimal policy as well as the optimal Q values or action values. And let's have a look at how this looks in practice. So the method that we presented in the last slide is actually called the SARSA algorithm. And the reason why we have this funny combination of letters is because we start in a particular state, having executed an action from the previous step. So this is not an action that we sample now. This is an action that came before in the last iteration. That's S and A. Then if we're there, we execute the action, we get a reward, and that's R. And we find ourselves in a new state, S prime. And remember that we don't use a transition model for this step. We actually have to execute the action and see what happens. And then from that new state, we can use epsilon greedy policy in order to sample the next action, A prime. And so this gives us a snapshot of a time step in a mission when we're leveraging the SARSA algorithm, and this is how it gets its name. So the main idea now is exactly the same in TD learning. We want to try to use bootstrapping. And except in this time, rather than bootstrapping on the state values, we want to bootstrap on these Q values or the action values. So basically, we want to include the fact that our policy is not given to us, but also include it as a variable in our value evaluations. And so we want to try to evaluate the policy by updating these action values. And remember, the names of action values, Q values, are similar, are the same. They basically account for the fact that we actually have an action that is also a variable that our value depends on. And we try to improve our policy, as we said, by sampling A prime in an epsilon greedy manner. So here is the update equation associated with SARSA. So again, just looking at it, it follows the same algorithmic structure as the TD algorithm. So again, we have some error here, and we have an existing value. The key difference, as we said, is now instead of the state value, we have the state action value or the Q value. So this is the value that we're trying to update. And with the one-step look ahead, we take the next reward. So looking at our structure of our problem, we have R here that came from executing the previous action. And we also have the Q value associated by performing the next action. Remember, A prime is obtained from the epsilon greedy algorithm, as well as the next state. And so over here, this gives us our error. And again, we want to move slowly in the direction of the error given our current estimate of the Q value. And this is basically the key concept behind the SARSA algorithm. It is essentially an analog of TD learning when we also account for actions. And remember, the actions are changed using the epsilon greedy algorithm over here in A prime. So looking at the pseudocode for SARSA, it is very similar to TD learning. Again, we see Q values appearing here in the update equation rather than just the state values. And we pick A prime, again, using the policy based on the epsilon greedy algorithm. So again, in terms of implementation, what we need to store here is simply a table of all these Q values. And then when we sample the policy, we leverage this table and see if we're going to exploit. We go to the one that gives us the maximum Q value from the given state. So we follow that action. Otherwise, if we pick to explore, we try an alternative random action to add exploratory behavior to our algorithm. And we need to repeat this procedure for every time step rather than every episode. So this is the main benefit of using these TD-based approaches, that we perform updates stepwise rather than episode-wise. This allows us to give faster convergence. And bootstrapping is happening here because whereas we actually observe the reward, we use the guess of the Q value at the next step based on the action that we sample in order to perform the update rule. So we essentially use our guess of the next state in order to improve our current guess. This is the main idea behind bootstrapping, and here again it's applied in the context of states and actions rather than just states. So following the trend from a model-free prediction, we can also say that we want to try to weight more frequent and more recent state-action pairs. So remember, we had this concept that states that appear more frequently are more important in terms of their contribution or their influence on the reward. And we also said that states that are more recent have the same importance, so they have more credibility on the final reward that we observe. So not surprisingly, the way to incorporate this for state action pairs in SARSA is again using eligibility traces. So here we have a copy of the same eligibility trace equations that we observed for TD lambda learning, except now we also account for the actions in our arguments. And so for every state action pair, we have a new table in addition to our Q values that tells us what is the eligibility trace of that state action pair. And every time we see the state action pair, we increment it by 1. Otherwise, we have the decay factor lambda, which exactly the same way as before, it decays the value of the state if we don't see it for a long time. So it adds this element of forgetfulness. So plugging the eligibility traces into our SARSA update rule, the important difference here is that we also have to multiply our error. Remember, our error is simply the difference of our bootstrapped Q value at the next time step and the reward, minus the difference of our current estimate for the state action pair. And we multiply it by the eligibility trace. This is like a factor that scales the importance of that state action pair. So again, exactly the same concept as previously, except this time we also have actions appearing because we want to keep track of actions coupled to states rather than just states. So we want to learn also the part that involves the agent making decisions and figuring out how they influence the values within our MDP. We call this approach SARSA lambda, not surprisingly, because it involves eligibility traces and the lambda decaying factor. And over here we can see the pseudocode, which follows the same principles of SARSA lambda, of the raw SARSA algorithm, except with lambda we also need to loop through all states and all actions. So we need to update also the states and the action pairs that were not associated with our episode, because we have the forgetting factor, which degrades or devalues the importance of that particular state action pair if it wasn't seen in the episode. Otherwise, the algorithmic core and the update proceeds in exactly the same way. We still sample the same policies using the epsilon greedy approach. In the final part of the lecture, we're going to look at doing model-free control when we have different policies for sampling and learning from. So there are two main paradigms for doing model-free control called on-policy and off-policy learning. On-policy learning operates with just one policy. It's the same policy that we're trying to learn as the one that we're sampling from. So a great example of this is SARSA, where we have the policy that we evaluate using TD-based techniques, and then we try to improve the same policy using epsilon greedy. However, this does not necessarily have to be the case. We can sample and learn different policies. This is what is done in off-policy learning. So this is the same as, for example, as if we had one robot or an agent looking at another robot or a human even trying to perform the same task. So whether our robot has one policy and another robot has the same policy, what we're trying to do is bridge the gap and see whether we can use that observed knowledge in order to improve the policy of our agent. So as you can see, off-policy learning could be very beneficial when we're learning from demonstration, for example. Alternatively, if we want to maintain one optimal policy, but also include another more aggressive exploratory policy. It could also be useful when we executed the same task in different circumstances and we're trying to bring that past history and knowledge in to improve our current policy. So the basic idea is to maintain different policies and in this way diversify our problem. So in off-policy learning we have two different policies, what's called the target policy as well as the behavior policy. And we'll see exactly how this comes into play in our update equations next. So we'll study just one approach for doing off-policy learning, and it's very commonly used in reinforcement learning called Q learning. So Q learning essentially learns the Q values in an off-policy way. So remember, we had two different types of policies. We have a behavior policy that we use to pick our next best actions. So behavior here implies what the agent is doing. So we're going to look at the distribution of actions in this policy and pick an action from it here. The big A corresponds to a random variable in a general case. But then, in order to do bootstrapping in the TD algorithm, we're going to adjust our TD target based on another policy, which is the target policy. So essentially that reward and our bootstrapping come from two different distributions of policies. And so our update rule in Q learning looks as follows. Again, we have the familiar structure of having the TD error as well as the value that we want to update. However, now here the bootstrapping of the next state action pair, remember the next guess of the state that we end up in, is actually coming from the target policy. Whereas the reward, or what we observe, is coming from the behavior policy, or the action that we just took. And the key insight in Q learning is that these policies do not have to be the same. Instead, we specify them in very particular ways. So we say that the target policy in Q learning is greedy with respect to the Q values, so the state action values. So whenever we want to figure out the value to use here in our update rule for the TD target, we always just look at our lookup table of the state action values and pick the maximum. So this is a greedy and deterministic algorithm as to how we develop the target policy in Q learning. In contrast, the behavior policy, we want to add some exploratory behavior there and say that it's epsilon greedy with respect to that same table that we have. So while our target policy is purely greedy and based only on our current knowledge of the Q values, we add some elements of exploration into the behavior policy. Remember, the target policy is the one that we use for bootstrapping. So if we plug that into our TD target from the previous slide, we can develop a new formulation of the target for Q learning. So here we have the general expression of the TD target we saw previously. And now we just substitute the definition of the next action based on the fact that we know that we're always acting in a greedy way. And so when bootstrapping with the target policy, since we're always acting greedily, we can just substitute the fact, this fact in our equations. And then we can simplify the expression as follows, where we take the maximum action corresponding to the Q value, and then the Q value of that, given that the action was taken, and it actually simplifies very elegantly to the fact that our TD target in Q learning reduces to the next reward plus the maximum Q value of the next action with some constant here. That constant is basically adjusting the changes in the update policy. So basically, if we draw a diagram like this, just like we did for SARSA, we see that the Q value is actually simply the maximum of the possible actions that we can take there. So in this lecture, we covered a lot of content on reinforcement learning and looked at a lot of methods. So in the final few minutes, we just want to do a quick recap to consolidate all this information and see how the different methods actually link together. So let's see a story of where we went in this lecture on reinforcement learning, where it took us. So we started by looking at methods of model-free prediction, which is how to evaluate the state values of an unknown MDP where we don't have any access to the models for the state transitions as well as the rewards. So an easy way of doing this was through Monte Carlo sampling, where we have episodic environment and we look at the values that we got from all the states, and then we computed the averages for all the states given all the returns. However, disadvantage of this approach was that it needed episodic environments, so we moved on to the other extreme to look at temporal different learning, which essentially bootstraps the estimates of the next state in order to update the current state and performs only a one-step look ahead. And this allowed us to do much faster updates to obtain convergence much faster, but it exploited this Bellman's equation and the Markov property of the MDP in doing so. Then we looked at the possible spectrum of n-step methods for model pre-prediction. So we said that instead of doing one step, as in TD-based, the TD0 algorithm, we could also do 2, 3, or n. So we tried to look at how we can obtain intermediate performance between TD and MC or Monte Carlo. We discussed how we can incorporate this parameter lambda in order to capture the effect of different time steps over time according to their recency. So we tried to decay the value of taking more steps to discount the value of information in the distant past. Then another improvement we made to our algorithms was to also consider the eligibility traces, which were all about counting the number of times a state appears and then using that as a factor of the importance of the update to that state. So moving on from prediction to control, we asked ourselves how we can get our agent to do actual decision making. And here we started by looking at methods of policy improvement. So if we have a policy, how we can perform new actions to discover new things and see if they lead to more promising results. Here the key approach that we considered was epsilon greedy, which uses probability principles in order to sample some exploratory actions from time to time, otherwise exploit the best known information. We then connected these concepts to Monte Carlo and temporal difference if we use them for policy evaluation. And we said that if we iterate through the cycle of evaluating the policy using these methods and improving it through a strategy such as epsilon greedy, we will actually converge to the optimal state action values or Q values as well as the optimal policy. We considered especially an algorithm called SARSA, which leverages the ideas of bootstrapping from TD learning and saw how we can get them to perform updates at every single step of an episode. Next, we brought in the ideas from model-free prediction on the lambda returns and eligibility in order to account for the frequency as well as the recency of this time the state action pairs in the SARSA algorithm. And this way we derived SARSA lambda. And finally, at the very end, we discussed the differences between off-policy and on-policy learning. And we said that off-policy is actually a method which allows us to maintain a diversity of the policies in our algorithm. And we looked at a special case called Q-learning that uses two different policies one, the target policy and the behavior policies, and always tries to pick the Q value associated with the next best possible state that gives the maximum possible Q value. So this brings us slowly to the end of this lecture on reinforcement learning. Here is just on one slide a summary of all the main concepts that we have covered. So important to recognize is the difference between model-free prediction and model-free control, and the analogs that we actually draw between them, because we can reuse the ideas on n-step and lambda returns as well as eligibility traces when we bring them from the domain of just prediction, so just finding out what our MDP is about and what are the state values, to the realm of control and decision making, where we also add the ability of the agent to make decisions and discover ultimately the optimal policy for it to execute its mission successfully. This was just a brief summary of reinforcement learning, but there is plenty of other reading out there, especially the book Reinforcement Learning: An Introduction and David Silver's reinforcement learning course, Introduction to Reinforcement Learning. We based a lot of the slides of this lecture and the main ideas on these resources, so please have a look into more details there.